Stoichiometry applications, our last complete chapter that we'll cover, probably, for the class, because the other chapters are also short. However, we just don't have time to get to them. Who remembers what stoichiometry is? And by who remembers, I mean who remembers the word stoichiometry and that we've used it before? Cool. We remember the word at the very least. That's good. So a little bit of a review. This chapter is like half stoichiometry review. So that's part of why I really wanted to go through it, because stoichiometry is a big word. It's a scary word for some of us, and it's a confusing word for some of us. So the basics of stoichiometry. Balanced chemical reactions, like this one given down below, give us a numerical relationship between reactants, things on the left side, and products, things on the right side. Good review. And these numbers, the number of, these are all molecules, or they can all count as molecules, number of molecules of those things. So we've got 3 H2 molecules reacting with 1 N2 molecule, and that produces 1 NH3 molecule. That should have a 2 in front of it. That's not balanced. Great. Now it's got a 2 there, and now it's balanced. Who made these slides? So number of molecules. More often, though, we use instead number of moles, which is just a very, very, very large number of molecules. That's our Avogadro's number of molecules. So how much nitrogen do we need to completely react if we've got 3 moles of hydrogen? We are looking for nitrogen. We're given 3 moles of hydrogen. Our goal is to go from hydrogen. We were provided a number for hydrogen. We've got 3 moles of it. We want to figure out how much nitrogen is that. Based on our balanced chemical reaction, 3 H2 reacts with 1 N2, and we can make a conversion factor, 1 N2 over 3 H2. We could also have moles in there if we wanted to. We could write it the other way around. So we can flip-flop it at any point, take the inverse. If the one that we have there is not correct, but it is the one that we want. So starting with our 3 moles of H2, we multiply by 1 N2 over 3 H2. The H2 parts cancel out, and we're taking our 3 moles, dividing it by 3, and our result is 1 mole of N2 that we need to put in to react with those H2s. That's about as simple as we can get in terms of stoichiometry problems. When we're talking about stoichiometry, we're talking about using this numerical relationship. How many of our reactants to how many of our products, or reactants to reactants, product to product, something like that. We can also do it with this one, which is also unbalanced. I'll have to go fix those at some point. If we get, this is a different type of problem, if 2 moles of NH3 are produced, how much of each reactant was used? So we've got 2 problems because we've got 2 reactants. In both cases, we're starting with our ammonia, our NH3, because that's the one that was provided. We were given a number. We're going from NH3, and I put the 2 in the wrong spot. This is awesome. Wow, incredible. All right, it's fixed. We're going from NH3 to H2 because that's one of our reactants. We're also going from NH3 to N2 because that's our other reactant. So our conversion factors for this first one, for the NH3 to H2, we're starting with NH3, so we need the NH3 on the bottom so it'll cancel out for units, dimensional analysis. And we need the H2 part as the other part of our conversion factor so that that's what we end up with. And for the other reactant, we've got our ammonia on the bottom and our N2 on the top. So the N2 is what we're left with, and the ammonia gets canceled out. So those would look something like this. We'd have 2 moles of NH3 times 3 over 2. So we would end up with 3 moles of N2 and in our other case, 2 moles of NH3 divided by 2, which would give us 1. This is the sort of stuff that we're doing when we're talking about stoichiometry. Usually we also have stuff added onto the front, like we might go from grams to moles, or we could go from liters to moles, or we could go from kilogram solvent to mole for using molality, our favorite. And we can also add stuff onto the back end. I don't know what's going on there. There are also instances where we will have limiting reactant problems. This is one way that we can make our stoichiometry a little bit more complicated. So in lots of industrial applications, you're going to have multiple things that are going into like a big batch reactor. And they might be added automatically, somebody might be adding them manually. Usually one of those things is going to be more expensive than the others. And you want to make sure that you're getting the bang for your buck. And so you're going to make that your limiting reactant. You're going to make it the thing that definitely runs out, definitely gets used up, or should, based on your reaction conditions. Sometimes the difference in price is like A will be like $10 a gallon, which you might think, wow, that's a lot of money. But B might be like $1,000 a gram, which is way more money, right? So we want to make sure that we're using up our $1,000 a gram thing, because if we leave half of it unreacted, we're leaving $500 of reactant that we've just basically thrown away. And so this is why we would want to do some limiting reactant stuff in a laboratory situation. So to find limiting reactants and theoretical yields, if we're starting with initial masses, we get to add a couple of steps. If we've got a reaction with titanium and chlorine gas to form titanium 4 chloride, we want to know what are the limiting reactant, what's the thing that runs out first, or makes the smallest amount of product, makes least product, and what's the theoretical yield if we start with some given numbers. The theoretical yield is how much is made or can be made, assuming everything goes perfectly, which it never does. The theoretical yield is the amount that we get out from our limiting reactant. So product from limiting reactant, LR. We are starting with 1.9 moles titanium, 3.5 moles chlorine. So we want to use stoichiometry. We are provided stuff in moles. We weren't asked like final amounts in grams, so we can also just answer these in moles. So just ramping it up a little bit in terms of difficulty. So we're going from moles of titanium and moles of chlorine to moles of titanium 4 chloride, TiCl4. Our limiting reactant is going to be the smaller yield, the smaller number, and the theoretical yield is going to be that smaller number. And we've got this on the next slide. So I like to set up these as two separate calculations, one over the other. So one for titanium, this 1.9 moles titanium, we'll do this as the first one because it comes first. And we're also doing 3.5 moles of Cl2. We want to know how much product we can make with either of these, with both of these. What's our product? What's our product?
Oh, I'm sorry. I got it.
TiCl4 is our product, right? So we're finding out how much TiCl4 we can make. So we need to know what's our ratio of, in this first one, titanium to TiCl4. Our ratio, if we look at the numbers in front of those chemicals, there's no number there. That means there's a 1. So it's a 1-to-1 ratio. Our conversion factor is going to be 1 mole TiCl4 over 1 mole Ti. So the of titanium cancel, and we're left with moles of titanium chloride, titanium 4 chloride. So the amount that we can make with our titanium is 1.9 moles TiCl. We also need to do it for our Cl2. So we've got 3.5 moles of Cl2. Our ratio is that we put in 2 Cl2s and we get out 1 TiCl4. So our ratio is 2 to 1. So the 2 Cl2, we'll add the moles in there because I know some people like it. 2 Cl2 on the bottom and 1 mole TiCl4 on the top. Again, this is so that our units cancel. So our moles of chlorine cancel out. We've got 1 on the top, 1 on the bottom, so those turn into a 1. They basically disappear. And we've got the moles of titanium 4 chloride on the top that gets pulled through. And so we have to do 3.5 divided by 2. We'll get 1.75-ish moles TiCl4. Which one of these two numbers is smaller? 1.75 is smaller, right? So this is our theoretical yield. It would be 1.8 moles of titanium 4 chloride for significant figures. 2 of them. And then what's our limiting reactant? Is our limiting reactant titanium or chlorine? It's the chlorine because the chlorine is the one that we use to make the theoretical yield. The chlorine runs out when we make 1.75 moles titanium 4 chloride. The titanium can make up to 1.9 moles, but that's assuming we have enough of the other thing, which we know because of the second calculation, we do not. So we would have a little bit of extra titanium left over. Our chlorine, though, is going to run out. So Cl2 is the limiting reactant. Questions? Okay, I'm going to turn you loose to try this one. Consider the reaction. If you begin with 2.4 moles of sodium and 1.3 moles of fluorine, what's the limiting reactant and theoretical yield of sodium fluoride in moles? All right, what is our limiting reactant?
Sodium.
We've got a guess for sodium as our limiting reactant. What's our theoretical yield of sodium fluoride in moles? We have a guess for 1.2 moles. Let's find out. So we've got two calculations because we have two reactants, two amounts that we're supplied with. If we begin with 2.4 moles of sodium going to sodium fluoride, and if we begin with 1.3 moles of fluorine, F2, and go to NaF. So 2.4 moles sodium, that's Na. Our ratio for sodium to sodium fluoride is 2 to 2. So we get 2 NaF out for every 2 Na that we put in. So the 2, because we've got one on the top and one on the bottom, we can cancel those out. We can also cancel out the sodium. It's basically a 1-to-1 ratio. And so our yield is going to be 2.4 moles NaF. This assumes that we have enough of the other thing, which we don't necessarily have. So we have to find out. And we've got 1.3 moles of fluorine, which is F2. How do we know that fluorine is F2? Let's Brinkelhoff would work.
Part of the H7.
Part of the horses need oats for clear brown eyes. It's the 4 clear brown eyes. That's one way that we would know. Okay, what's our ratio of F2 to NAF? How many F2s do we put in? We put in 1 F2. We've got an invisible 1 in front of our F2. Put in 1 F2, and we would get out 2 NAF. So the F2s cancel. We're multiplying by 2, so it would be 2.6 moles NAF based on our starting amount of fluorine. However, this assumes that we have enough of the other thing, and we know, because our yield that we calculated for the previous part is 2.4, we know that we don't have enough to make 2.6 moles of sodium fluoride. Our sodium is going to run out first. That makes sodium the limiting reactant, and our theoretical yield is 2.4 moles. Questions about how we did any of that? You will have to do this on the final, which is true for like almost anything that I say in the class, but this will show up in like multiple ways, the stoichiometry stuff. All right, we are nonfiction writing about stoichiometry. Let's increase our difficulty, prose at stoichiometry. So another example, usually we will be starting with grams, or we'll be starting with some other unit. We're not just given moles, because we can't directly measure out moles in a lab setting, and so it's more likely that we're going to start with grams. If we have this many grams of sodium, this many grams of chlorine, what are the limiting reactant and theoretical yield? So it's the same sort of setup. However, we're not starting with moles, so we have to get to moles first. How do we get from grams, which we have, to moles? We need stoichiometry. We need molar mass. So we're going to set up the calculation the same way. We've got 53.2 grams sodium on the top. Our second calculation, we're starting with 65.8 grams Cl2 on the top. And we need our molar mass for sodium and for Cl2. For sodium, we refer to our periodic table. It's 22.99 grams per mole. To get the units to cancel out, we put the 22.99 and the grams on the bottom, because those are always paired together. The moles goes to the top. The grams will cancel. For Cl2, a little bit of math involved. Right, we've got 2 Cls. Each Cl is going to be 35.45 grams per mole. So Cl2, 70.90 grams per mole. Same idea, we're going to divide by our molar mass, so the grams cancel. And I know that some of you like to do things in multiple steps rather than putting it all at the same time, so we'll go ahead and do that this time. So we would have 2.314 and change moles sodium, Na. This would have 3 significant figures. For our chlorine, we would get out 0.928 ... moles Cl2. And now we've come to the stoichiometry step. All right, so we have moles. We can use moles in our balanced chemical equation. We know that it's balanced because it's got coefficients. We can also check it for ourselves because sometimes I don't balance them correctly, apparently, as we saw previously. Okay, so our ratio for sodium, 2 sodium in, 2 sodium chloride out. For chlorine, 1 chlorine in, 2 sodium chloride out. So our ratio is 1 to 2. So we'll apply these ratios for our sodium. 2 to 2 is the same as 1 to 1. But we should be diligent and write it out anyway. So 2 NaCl on top, 2 Na on the bottom. The 2's cancel, the Na cancels. And it's just going to be 2.314 ... moles NaCl. We could round that to 2.31 moles salt. For our Cl2, our chlorine, 1 chlorine in, 2 sodium chlorides out. So the 2 NaCl is on top. The 1 Cl2 is on the bottom. The Cl2's cancel. And we are multiplying by 2. Be 1.856 moles sodium chloride. We would round that to 1.86 moles sodium chloride, table salt. Which chemical is our limiting reactant? Is it sodium? Is it chlorine? Is it sodium chloride? It is chlorine. It's Cl2, chlorine, because that produces the smallest amount of sodium chloride. So Cl2 is the limiting reactant, and this 1.86 moles is our theoretical yield. If everything goes perfectly, we'll make 1.86 moles of sodium chloride. I stopped it at moles. I meant to go to grams. It doesn't really matter because it didn't ask for a specific unit, so this would also be fine. On an exam, it'll always tell you what units you're supposed to provide. Questions? Cool, we're crushing it with the review then. Here's one for you to try. What maximum amount of ammonia in grams, it specifies, can be synthesized from given amounts of N2 and H2? And I balanced it correctly here. Okay, we are looking for the maximum amount of ammonia in units of grams. So we're trying to get to grams of ammonia, that's NH3. We're given 2 starting materials, grams of N2. So 25.2 grams N2, and also 8.42 grams of H2. These have different ratios with our NH3, right, based on our balanced chemical equation. So we'll need to do a couple of things, right? We're starting with grams. To use our balanced chemical equation, we need to have moles. So we need moles for the stoichiometry step. And we have grams currently, so we'll have to get to moles. Grams to moles, we're using molar mass. So we'll have to divide by 28.014 grams per mole for N2, because we've got 2 nitrogens at 14.007 each. The grams will cancel and we'll have moles. For H2, we're going to divide by 2.016 grams per mole. 2 hydrogens with 1.008 grams per mole each. And then, if we stop there, we'll be in moles of our starting materials, which means that we can use our balanced chemical equation. We can use the coefficients to calculate moles of our products. So one of them, H2 to NH3. For our H2, that's down here, We put in 3 moles of H2, we get out 2 moles of NH3. So the 2 NH3 goes on the top, the 3 H2 goes on the bottom, the H2s cancel, and we would have units of moles of NH3 if we stopped here. We are also doing N2 to NH3. 1 N2 in equals 2 NH3 out. 2 NH3 on the top, 1 N2 on the bottom, so the units cancel. Questions so far? Yes?
Why is it that we convert it to moles whenever the final answer should be in grams?
We convert it to moles because we have to have moles to use the balanced chemical equation. Because when we're talking about a balanced chemical equation, this is 3 H2s. We can talk about that as like individual H2 molecules, or we can scale it up to moles. But it has to be in like the actual number of things that we have. And if we're talking about grams, if we have grams, that's not the number of things we have, that's the amount, like the mass of what we have. So like if you go to the grocery store and there's like, I don't know, you're buying different types of squash or pumpkins, right? There's some really small squash, there's some really big squash. If you're paying by the pound, you're not going to get very many squash if they're like the giant pumpkins versus like the little tiny ones that I buy for my wife every fall because she thinks they're cute. Those ones you can get a lot of bang for your buck if you're paying by the pound. So I'm going to get, for 20 bucks, I'm going to get maybe 2 big pumpkins, or I'm going to get like 10 little squash. And then you can throw them all over the house. Very decorative, very seasonal, very festive. Other questions? Cool. We are going to go another step though, because we have to get to grams of NH3. So we also need a molar mass for NH3. For NH3, we've got a nitrogen, and we've also got 3 hydrogens. So our calculation should look something like this. We're putting into our calculator 14.007 plus 3 times 1.008. You should get out something that resembles 17. .031 grams per mole. How many significant figures? I'm just kidding. We don't care about significant figures for molar masses. Some of you got scared. Okay, so multiply by 17.031 grams per mole for both of these. The moles cancel, this moles cancels this moles, and we'll be left with grams of NH3. Everything else has been canceled out. And then to put this all into our calculator in one step, multiply everything on the top, 25.2 times 2 times 17.031, then divide by things on the bottom, 28.014. And for the N2 part, the top one, 30.6 after we round. For the bottom, we're doing 8.42 times 2 times 17.031, divide by the things on the bottom. We get 47.4 grams NH3 after we round for 3 significant figures. Just a note for these, for the second calculation, we've got 2 things on the bottom. You have to either multiply these in parentheses. So you would do 8.42 times 2 times 17.031, divide by, and then put the 2.016 times 3 in parentheses. Or you can divide by 2.016 and then also divide by 3. And then you don't use parentheses. You should get 47.4 grams NH3. Questions? Yes.
I did it similarly, but I didn't, for some reason, know that you could just add like the mole and mass to both of them at the end, like one whole step. I like broke it up into 3 steps.
Mm-hmm.
Once I got the moles for N2, I saw that it was less, and I just converted that to grams. Would I need to convert the hydrogen to grams if I already see the moles is less?
Yeah, so one of the shortcuts, that's a shortcut
Oh,
that you
okay.
can do. If we can probably all see, right? The last step is exactly the same. We're multiplying by 17.031 grams per mole. If you wanted to, if you did this as separate steps, you could leave this step off. You'd find the moles of NH3 instead of the grams, just the moles of NH3. And then whichever one's smaller, that's the one that you could take forward. Optional. Okay, what is the maximum amount? What's the largest amount of ammonia that we can make in grams? It is 30.6. This is our theoretical yield. Our limiting reactant, if we were asked, would be N2. The reason this is the maximum amount that we can make is because we run out of the N2 once we get to 30.6 grams made. So we don't have enough N2 to get to this 47 grams of ammonia. This is like if we're going back to our BLT recipe, right? If we've got 4 slices of bacon and we need 4 slices of bacon for each BLT, even if we've got 10 loaves of bread and plenty of fish and other things that you might put in a BLT, right? We're going to run out of bacon before we can make more than 1 BLT. Fish is a crazy thing to put on a BLT. Okay, new stuff. Jumping from slide 10 to slide 12 somehow. Enthalpy change. Oh, there's probably a hidden slide. Enthalpy change is a measure of heat evolved or absorbed. Evolved meaning produced, absorbed meaning absorbed, taken in. So chemical reactions can be exothermic, exo like out, where they emit thermal energy. Or they can be endothermic, where they absorb energy when they occur. Who can think of a place where the exo prefix shows up? Another word that starts with exo. Exoskeleton. What has exoskeleton? Insects, bugs. They've got their hard crunchy bits on the outside, right? That's the exoskeleton. They've got basically their bones, their chitin is on the outside. Our bones, where are our bones? Inside. Our crunchy bits are on the inside. We've got, if we use the same exo-endo, we've got endoskeletons. So exo like on the outside, the heat is on the outside, it's going out. Endothermic, the heat is knocking its water bottle over on the inside. And scene. So the amount, the enthalpy part, because enthalpy is a crazy word, right? The amount of thermal energy emitted, exothermic, or absorbed, endothermic, by a chemical reaction can be quantified. We put a number to it with a function called enthalpy. So we have this term, enthalpy of reaction. Enthalpy here is the delta H, and the reaction gets shortened to RxN for some reason. This is the amount of thermal energy, or heat, so H could also stand for heat, that flows when a reaction occurs at constant pressure. The constant pressure part, not really that important for us. So delta H can have a sign, positive or negative. And this depends on the direction that the energy flows. A negative for delta H of Rxn means heat, energy, leaves, flows out. This is sort of like when you participate in the economy, you buy yourself a Starbucks double shot from the student store, right? You go and you look at your bank statement, or you look at your wallet and you count your cash, right? It's negative compared to what it was previously. You've withdrawn some money in exchange for that caffeine and the tasty flavors. If you get paid, love getting paid, that's like energy flowing into the system, and you're going to see that without a negative sign in front of it because we just assume that if there's no negative, it's positive. So positive for delta H means energy flows in or is absorbed. We're adding energy, we're adding heat to our heat energy bank account. It's going to have a positive sign. These are the same as exothermic and endothermic. For an endothermic reaction, our system, the system is just the thing that we care about. Usually that's our chemical system. So in our little batch of chemicals, if the delta H is positive, that means energy is flowing in. We're making an energy deposit into our chemical system. So the chemicals absorb energy. Hate it. Absorb energy. In an exothermic situation, our delta H is less than 0, meaning it's negative. So the chemicals release energy. The surroundings would then absorb that energy and get warmer. In the case of the endothermic reaction, the surroundings get cooler because they're putting energy into the chemical system. Some examples. Delta H is negative for exothermic reactions. Negative delta H means that it's exothermic, energy is flowing out, and combustion is typically what we talk about when we talk about exothermic reactions. So CH4, which is the main component of natural gas, is methane. It can go through combustion with this balanced chemical equation, and the delta H is negative. So this negative sign means that it is exothermic. (802.3 kilojoules heat emitted). And secretly, this is per mole coefficients that we see in our balanced chemical equation. So when 1 mole of CH4 reacts with 2 moles of O2, this negative 802.3 kilojoules is released. Delta H of the reaction is basically another coefficient for stoichiometry. So we can do some stoichiometry, sort of, to go from moles of any of our chemicals in our reaction to heat. We can also have a positive delta H. Delta H is positive for an endothermic reaction because heat is going in, heat is being absorbed. And we see that with this reaction between nitrogen and oxygen to form nitrogen monoxide. It's got a positive sign in front of it. You will probably, if this shows up on an exam, probably will show up on our final, you'd probably just see the number instead of having a plus in front of it. If there's no negative, it's positive. And again, we can treat this like a coefficient for stoichiometry purposes. If we react 1 mole of N2, because that's the coefficient in front of the N2, with 1 mole of O2, that will absorb 182.6 kilojoules. Will also produce 2 moles of NO2. Questions? Cool. So the amount of heat emitted or absorbed depends on the amounts of reactants that actually react. If I have a small stack of wood on my desk and I light it on fire, I'm going to get in trouble because I shouldn't be setting fires in the classroom. If I set a large stack of wood on my desk and I light it on fire, I'm going to get in more or less trouble? More trouble because it's a larger stack of wood, right? It's going to produce a bigger fire. I might burn down the whole campus, which is a crazy thing to take out of context. That's why Logan's laughing. Nobody stole my red stapler, so I'm not going to do that. So little stack of fire, right? Little stack of wood produces a small fire, produces a little bit of heat. Big stack of wood, we've got a bonfire, right? That's going to produce a lot of heat because we've got more reactant that's going in. We are usually going to specify delta H of the reaction with a balanced chemical equation for the reaction. That delta H, the size, the magnitude, pop, of delta H is for the stoichiometric amounts of reactants and products as written. So whatever amounts that we have written in, usually we're just given this as a balanced chemical equation, which is cool. So example, liquid propane. We've got a balanced chemical equation. We've got a delta H for the combustion of propane. We have 1 propane reacting with 5 oxygen molecules to produce 3 CO2 molecules and 4 water molecules. The delta H value is negative 2,044 kilojoules. We can make so many conversion factors. This tells us that when 1 mole of C3H8 reacts with 5 moles of O2, we form 3 moles of CO2 and 4 moles of H2O, and 2,044 kilojoules of heat are emitted. Negative means exothermic. Heat is put outside. So we can make some ratios. Let's just make the ratios in one direction that have the 2,044 kilojoules of heat. So we are going to take our C3H8, our negative 2,044 kilojoules, negative 2,044 kilojoules of heat. The other part of the conversion factor would be C3H8, 1 mole C3H8. We can also do this with our O2, negative 2,044 kilojoules per mole, and that moles is 5 moles of O2. So if you put in 5 moles of oxygen, you'll get out this amount of heat. If you put in half this amount of oxygen, if you put in 2.5 moles of O2, it's going to be, that's half of this moles of O2, it's going to be half this amount of heat. So it scales based on the amount that we actually put in. We can also do it for the products. So 3 CO2. If we produce 3 CO2, 3 moles of CO2, that will also be corresponding with 2,044 kilojoules of heat being emitted. It also scales with water. So negative 2,044 kilojoules per 4 moles of water produced. You could, of course, flip all of these if you wanted to, top and bottom. Usually we wouldn't be making all 4 of these, but these are the 4 that we can make that relate to heat. Usually you just make the one that you need. All right, some examples, some calculations. Ammonia reacts with oxygen according to this equation. Calculate, what are we calculating? Heat. We're finding heat in kilojoules associated with the complete reaction of 97.32 grams NH3. So we care about what two things in our balanced chemical equation? What are the two things we care about?
NH3.
NH3 is one of them. Underline it. What's the other thing we care about? Heat, kilojoules. All right, this negative 906 kilojoules. We're going to put those together to make our conversion factor. So our conversion factor, negative 906 kilojoules for moles NH3. Right, that's the one conversion factor that we need to construct. We don't have to do anything else here. We don't have to make the other three like we did on the previous problem, or the previous slide. So starting with our grams of ammonia, because that's what we were given. We're trying to get to kilojoules at the end. If we're trying to get to kilojoules, we've got a conversion factor between kilojoules and moles of NH3. So we can get to kilojoules, but we have to have moles of NH3. Do we know how many moles of NH3 we have? Not yet, but we can find out. How can we find out? How can we get moles from grams? Molar mass. So we're going to use our molar mass for NH3. We saw it earlier. So we're going to divide by our molar mass. So the grams and the number go on the bottom. The moles goes on the top. Grams cancel. If we stopped here, we would have moles of NH3. Then we use our ratio. Whoop. Because of our ratio, the NH3 and the moles cancel, and the kilojoules is all that's left. So plug in the calculator, 97.32 times negative 906, divide by 17.031. Who's got an answer? Did anyone get syntax error? If you got syntax error, hopefully you figured out that's not the correct answer. You used the minus instead of the negative number, which is cool. So negative 5,177.14287 kilojoules. We would round this for 4 significant figures. Negative 5,177 kilojoules. If we, for some crazy reason, did this reaction in our hands, I don't know how we would do that. If we did this reaction just like in the palms of our hands, would our hands feel cold or hot? It's a negative number for heat, so that means it's exothermic, that's heat going out, so our hands would probably feel hot. We would be absorbing the energy. Our hands would be the surroundings. The system is the reaction that we see here. So our hands would probably get really hot. I'm guessing that we would burn ourselves. Not great. So this is exothermic. Heat released, emitted. Questions?
Did you divide by 4 at the end?
I did not divide by 4 at the end. And many of you didn't catch it. You failed. The rest of you who did catch it, congratulations. Great work. Negative 1,294 and some numbers after that also. So that number, our hands would actually be 1/4 as burnt as we thought they would be, which is great news for us. Other questions? All right, this is one for you to do. Good luck. All right. We are looking for enthalpy change. What's enthalpy? What's our answer units going to be like? Grams, moles, liters, kilojoules, atmospheres, millimeters mercury. Yeah, it's going to be kilojoules, right? Enthalpy change. Enthalpy, basically heat. So we're looking for heat, just whatever that number is, whatever we get out. And we're looking for the amount that occurs when 58 grams of sulfur dioxide reacts with excess oxygen. We've got a couple of sulfur compounds. Which one is sulfur dioxide? Is it SO2 or is it SO3? It's SO2. We know that it's SO2 because it's sulfur dioxide. Our other hint is that it's reacting, so it's on the reactant side. So we are going to be using this 58 grams SO2 to find kilojoules. We need something that relates kilojoules and SO2, and we've got this conversion factor that we can make, negative 198 kilojoules for every 2 moles SO2 that reacts. To be able to use this conversion factor, what do we need? We need moles. We have grams. We can get from grams to moles with molar mass. For sulfur, it's 32.06. So add those up. 64.058 grams per mole. Going to divide, so our units cancel grams, and then the SO2 and the moles will also cancel. We do 58 times negative 198 divided by our molar mass, also divided by, importantly, 2. And our kilojoules, negative 89.637 ... Round it for 3 sig figs, negative 89.6 kilojoules. Questions at all? Sometimes, if you haven't done the homework yet for this, the absolute value of heat might be requested. And there could be words that are used to convey whether it's a positive or a negative sign. Remember, this chapter, especially the first 10 slides, the review part, will show up on the final. The new stuff will also show up on the final.